recall.
Dr. Wu, just to verify, for
Mhm.
our presentations, what time should we be aiming for? About 10, 15 minutes we're talking, or?
You mean the
Yeah, for like the,
MD one?
no, the
25 minutes.
25 minutes, okay.
Okay, so probably let's start. So hello, everybody. Today we will have Mark Zhao as our guest speaker. So Mark is a PhD student at Stanford, advised by Christos Kozirakis. And his research centers around co-design systems and hardware to improve the scalability, performance, and security of data center scale application like machine learning. He was recently a visiting researcher at Meta, and where he worked on data infrastructure for machine learning training. He received his bachelor in ECE at Cornell, where he worked with Eddie Su on hardware security. Mark is generously supported by a Stanford graduate fellowship and a Meta PhD fellowship in AI software hardware co-design. So the mic is yours.
Yeah, thanks everyone. I know it's
wait,
like there on yeah.
Please share the screen. It's not.
Yeah,
Not sharing.
gotcha. Yeah, thank you everyone. I know it's wait, that looks good, right?
Mhm.
Yeah, cool. Yeah, I know it's late on the East Coast and maybe a holiday, but I really appreciate everyone kind of coming out and attending this. I think I want to just start off by saying, please feel free to interrupt, ask questions. I much prefer like a discussion rather than just like me talking for however long. And I believe like so I have until what, like 7:15, right? Like this definitely won't take that long.
Yeah.
But just trying to scope it out. Okay. Uh yeah, so please feel free to interrupt and I'll pace as needed. Cool. Yeah. So today I like to talk about some of our work on really understanding and trying to design, build, and scale all of this kind of infrastructure that we need to manage data for really large scale machine learning deployment. So a lot of this work reflects kind of published work that we had when I was at Meta for a few years. I should say that I'm, no longer there anymore. This is all like my point of view. I'm not, speaking on behalf of them and things like that. But yeah, so I think to just get started, I probably don't need to tell anyone this, but in the past year or so, we've seen kind of this new, explosion in terms of how much AI and machine learning in general is really revolutionizing a whole bunch of different domains, right? So not only do we have these really impactful large language models and foundation models, but ML is used anywhere from medicine all the way to digital agriculture and beyond. As I mentioned, a lot of this, pretty much all of this talk will focus on work we did at Meta. And Meta specifically, the primary class of ML models, or arguably the most important class of ML models, are these deep learning recommendation models, or DLRMs. And I think Dee mentioned that you guys have looked at recommendation a bit in this course, so feel free to tell me to skip anything that's not relevant or ask questions and things like that. But at a high level, these recommendation models are used to suggest new and meaningful content for users. You can imagine because of their importance, they underlie a lot of important services such as Instagram Reels, Facebook newsfeed, etc. And again, because of just how important these models are, they actually take a large majority of the AI training demand across the fleet at Meta. And kind of this fleet, this infrastructure is what I want to, dive into today, right? What do we need to support these models? And if we kind of zoom out and look at it from kind of the industry like perspective overall, what we've seen over the past, few years, and especially very recently, is this trend towards training larger models and more complex models, right? Models that can do more advanced things. And what's really enabled all of this, as I'm showing in the left here, is how much compute effectively we're able to provide towards training these models, right? So maybe some of you have seen this this plot or similar one like it before, but the y-axis is how much compute we need to train a model to convergence. The x-axis is how recent these models were. And kind of the takeaway here is that this amount of compute that we need to train better models is really outpacing even Moore's law, right? We've seen this massive growth in terms of the infrastructure we need. So kind of the takeaway here is not only do we need the benefits from kind of Moore's law in terms of scale up infrastructure, meaning faster GPUs, newer generations of domain specific hardware, and things like that, but we also need scale out infrastructure, meaning we need data centers of tens of thousands of GPUs and beyond in order to supply enough compute resources to meet these demands. And kind of the main points I want to make in this talk is, if we look at what this infrastructure looks like, contrary to maybe popular belief, but it's much more than just a bunch of accelerators, right? We don't really take tens of thousands of GPUs and stitch them together and that's your training data center. There's lots of different components around all of these GPUs that really make everything work. So to kind of start off this entire ML pipeline that we use in industry, we really start with this data storage and ingestion component, which would take real world interactions, generate training data from it, pre-process that data, and then do we train the models, right? So this pipeline gives us tensors, training data that we feed into a bunch of different machine learning jobs, training jobs, which produce models. We evaluate the models to see which one's the best. And then of course we deploy the best one into production, right? And then we run inference on it. And through inference, through interacting with the real world, we generate more data, and the cycle is just continuously occurring, right? And what I want to focus on today is this first component, like what do we need to support these massive training jobs? And specifically, it's this DSI or data storage and ingestion pipeline that consists of a ton of different services, infrastructure components to, at a very high level, generate, store, and pre-process tons and tons of data for these ML jobs. I want to stop and see if there's any questions. Feel free to interrupt or anything. Okay. So maybe I can start off by saying, why do we care about all of these components, right? And the fact is that this DSI stuff, this infrastructure is a huge proportion of a data center's training capacity, right? How many, in terms of capacity, I mean, how much stuff do we have in a data center that we can use to train these models? So specifically, if you take a look at the left graph, what I'm showing are 3 production recommendation models at Meta on the y-axis, and the x-axis is a breakdown of how much capacity, pretty much how many servers effectively, are needed to support training these different models, broken up by storage, pre-processing, and training resources, right? So the takeaway here is that, the training part, the GPUs, for a lot of these models are largely overshadowed by the storage, the pre-processing components of this entire pipeline. And not only are these components huge, but they're also increasing in demand, right? The right graph here is just showing over the course of 2 years how much growth we've seen at Meta in terms of both the dataset storage size, so doubling, and also the pre-processing bandwidth that we need, so growing over 3 to 4 times over the course of 2 years. But if we kind of like parallel how much focus there is on training versus DSI, we've seen both in terms of, industry and also academic conferences, much more focus has been dedicated to just the training components, right? And kind of the thesis of this talk is really, in order to continue scaling all of this infrastructure, we really need to focus on the whole picture. And so I want to kind of dive in and give you an overview of A, what this whole picture looks like, and B, what are some kind of lessons that we've learned or some approaches that we've taken to start optimizing this end-to-end pipeline. So this talk is going to kind of dive into two main sections sourced from 3 papers that we've published recently. In the first half, I'll talk about, again, what does a DSI pipeline look like? What are some key takeaways that we've done by just going super deep into analyzing, Meta's DSI infrastructure? And then there will be a short kind of aside to talk about some interesting things we can do in the storage stack based on some of these lessons that we found. And then in the second half, I'll just go really deep into talking about, hey, now that we've understood these lessons, how can we optimize all of these different components end to end via kind of a co-design approach. So before starting the first part, any questions?
So I have a question about the trend of the storage size and online ingestion bandwidth. So you know what caused the change? I mean the gap. I mean at the beginning it looks they're very close to each other, but over time the gap is larger.
So it's a bit hard to hear, but do you mean like the slide on the right?
Right.
Where the graph, kind of what the difference in the gap is?
Yeah.
Yeah, so that is, so to kind of understand how these models are trained in industry, typically what happens is that there's a model type that you have in terms of, so to give a concrete example, for example, like the Instagram, Reels recommendation will have a specific model type. And for that model type, there will be a ton of different model variants or training jobs that are run to produce a new like instance of a specific model for that task, right? If that makes sense. And so what we've seen as time progressed is just that this scale out has really scaled out. So there's been more and more and more GPUs provisioned into these data centers used to support these models. And so for each model type, there will be a specific data set, right? And what happens is that now people have access to more and more GPUs. They're able to launch more like hyperparameter tuning jobs or concurrent training jobs for that specific model type. So all of those training jobs for a given model type read the same data set. And so the storage pressure is a bit less, while as you buy more and more GPUs, kind of the number of times the specific sample is read is growing up and up, right? So kind of they're both increasing because larger models need more data, but also it just seems that like Meta's able to buy more GPUs, and that is just outpacing. That's just scaling up the amount of IO that we need.
Okay. That sounds pretty much makes sense. People are able to make the training more parallelized, but the data storage is not that kind of scalable as a compute, right?
Yeah, and I'll talk about how we scale the storage aspect. But yeah, this IO pressure, like the fact that GPUs are just so IO intensive, and you throw in another GPU, and that's like more IO that you need to support from your storage stack, is a big issue.
Okay, thanks.
What caused that giant spike down in the early stage of 4 to 2?
That's a good question. I'm not totally sure if I don't know the answers on the off the top of my head. Maybe like yeah, I don't I'm not sure. I don't want to speculate.
Okay, you're fine.
Yeah. That's a good question.
Hey,
Yep.
this is Professor Wang. So maybe you are going to mention it and the infrastructure DSI. And this, what is that? Are they using the cluster file system? Like what specific parallel file system they're using to
Yeah.
implement the data? Maybe you will mention later, right?
Yeah, I'll go over it a bit later, but just to kind of to give you an answer now. So Meta has a file system called Tectonic that runs on just hard drives. So it kind of evolved from HDFS and through a few iterations grew into this file system called Tectonic. It's a distributed file system that kind of has similar semantics to HDFS, but is a lot more scalable. So all of it runs on distributed hard drive based storage nodes. Yeah.
Oh, that sounds okay. I saw the HDFS is not for high performance, but maybe because the data still rely on the locally directly attached storage, right? Instead of a network attached storage.
No,
Or
everything is over the network. So all of
oh,
the data is within a cluster in each data center. So all the services in a data center read data over the data center network from that cluster.
from the cluster, but you have a separate GPU cluster, right? GPU cluster is discrete, right? I guess.
Yeah, so the GPU cluster, the ingestion, the data set is read from the main data center network that stores all of the data.
I don't know.
Makes
You need
sense.
to have a future slides like showing the overall architecture, right? I guess, but that's
A bit, but if there's any, so maybe I can like go over that information, and then if there's still questions, I can
yeah,
come
that's
circle
fine.
back. Okay.
Okay, thank you.
Yeah, so I think to start off with, the first half of this talk is really what can we learn from these DSI pipelines? And of course, the first kind of takeaway that I'll go over is really the DSI pipeline really needs to be disaggregated. And so if we take a look at a normal kind of training pipeline for something like MLPerf, what do we see, right? So if we want to run an MLPerf benchmark, maybe we'll start with a data set like ImageNet. We'll, put it in a cloud storage like an S3 bucket or something similar to that. And then once we want to train the model, we'll use our fancy new accelerator server, something like an NVIDIA DGX machine, right? And then maybe touching on the storage part here, but in these applications, we'll typically download this entire data set to local storage, something like NVMe, right? And then we'll do some pre-processing to clean up the data a bit, and then we'll start our training job. And once we start our training job, we'll do more pre-processing using the host CPUs, right? The CPU nodes that are on the server itself. They'll apply some transformations, turn all of this data into tensors, and then throughout the lifetime of the training job, we'll load those tensors onto the GPUs, and the GPUs will train the model, right? But this picture doesn't work in kind of industrial applications for a few reasons. The first reason is if we take a look at our data set sizes, right? And what we see here is that for these models, we need tens of petabytes of data. And these numbers are actually a few years old, so it's probably even more now. But the point here is that we can't possibly fit all of this data locally into our GPU nodes. So again, we have to kind of store them somewhere else, in this case, over the network in our distributed file system. And I'll go into a bit more detail about that later. But coming back here, the second problem is not only is storage not enough, but the pre-processing compute resources that we need are huge, right? What the table I'm showing you here is the number of x86 sockets, right? So actual sockets. We need to supply enough pre-processing bandwidth for each 8 GPU training node. So you can see we need dozens of x86 sockets in order to feed the GPUs, just because they need so much data at such a high bandwidth, right? And if we look at kind of our DGX machine, it has 2, maybe 4 sockets, and that's just not enough. And kind of what happens in this case, if we under provision our server here, is the GPUs, the really expensive A100s, H100s, whatever, are spent stalled waiting for data to come in, and you're just underutilizing all of your GPU cores, right? Because of all of this upstream infrastructure isn't right. And so the takeaway here is that we really need to disaggregate all of these upstream resources to eliminate all of these data stalls and really right size the resources that we have for each training job. And kind of going over what this looks like at Meta, you know, I'll kind of cover this entire pipeline. So within each data center, our training pipeline really starts with a data generation and storage tier. So what this means is that from the real world events that we have, all of that data goes into kind of this feature engineering pipeline. You may have heard of that term before, but what that means is, you know, these are just a bunch of ETL jobs. So things like Spark jobs, right? That take raw data, clean it up a bit, and then kind of schematize it. And these jobs outputs massive Hive data sets, so structured database tables that are put into a file system called Tectonic. And so these tables, to go in a bit more detail, are stored as you know, columnar files. So if you've heard of things like Orc or Parquet, we break up each of these massive Hive tables into thousands and thousands of columnar files, and just you know, dump all of that data into this distributed file system called Tectonic. Then for each training job, we'll launch a tier of reader workers. These workers are called DPP workers. And each worker, what they'll do is they'll read the data from this distributed file system over the network. They'll do some cleaning, some filtering. For example, if a feature is not needed, we'll drop the feature. Then these workers will transform batches of samples into tensors, right? Because, you know, the ML framework understands tensors and not, you know, database tables. These tensors are then fed to a tier of trainers. So it's important to note that the training tier and the reading tier, the DPP tier, are kind of gang scheduled together. And so, you know, we'll launch one server of GPUs and, you know, 2 workers collectively. And throughout the lifetime of the training job, this DPP worker will be continuously reading the data set, pre-processing it, and feeding it to the trainer. Something important to note in terms of what you know, industry implications is that, as I mentioned before, there's lots of different types of machine learning models that are being used across the company, and all of those models need to be trained. And so all of these different types of training jobs, all of their different characteristics are being run on shared infrastructure, which creates some interesting characteristics, which I'll talk about a bit later. But while at this picture, any questions? Okay.
So, hey,
Yep.
can you go back? Yeah. So this picture is looks like, yeah, Hive is really the lightweight database, right? The abstraction on top of the Hadoop file system. What is exactly the Tectonic file system? Is a parallel file system? Is it the extended version of the Hadoop, or because maybe you don't need to deal with that level, right? Because to me, I'm a parallel file system, cluster file system people. Like I did this for a long time. And this looks like it's a more internal cloud, right? Internal,
Yeah. Yeah.
cloud
So I mean, all of this is
and
Meta internal specific, this is all internal. Yeah.
Yeah, all these, see, you describe some nice like workflow pipeline. This is a very high level, you know, uh, functions, right? High level and what they do. But I guess those are not, because I don't know, some special, maybe the tectonic file system is not kind of special, right? It's not that, it's a parallel file system or distributed file system, or is a virtual distributed file system. What exactly is that?
It's a distributed file system. So for more detail, there's a paper in FAST in 2020 you can refer
Oh,
to.
oh,
But at a
okay.
yeah.
Did you, or is it from your group? They published your first paper, 2020?
No, that was like the storage team at Meta. So the tectonic file system, I should say, underlies pretty much all of Meta's data.
Okay.
So things like videos, images, all the way to like Hive tables, all of that data is stored within this. There's a shared storage layer at Meta,
I
and
see.
that's called Tectonic. And so that gives you a very basic, append only kind of p-read IO interface. And all of the
POSIX, something that's POSIX compliant, or I don't, they mean, they
it's
may
not
have,
exactly
yeah.
POSIX compliant, but like a very basic, very basic interface. But all of the infrastructure on top, so every single service kind of builds layers of abstraction on top of that to meet their needs. So, things like images and videos have their own kind of storage stack, and things like data warehouse has its own storage stack, but at the very base, it's all Tectonic.
Because I'm just curious. I know this is Meta as a commercial products, but there's other like object storage, right? I mean, like Amazon, they use their own object storage stuff to deal with this. I'm curious why they choose this tectonic file system, distributed file system to build their
Yeah, so I
pipeline.
mean, I think as I mentioned, kind of every single piece of data is stored in this file system. So that's just kind of how it works. And
This is only for one site, I guess. You don't need the like because Meta, when they serve 33 billion users, right? And they should have some like different servers. This is only for the recommendation system, right? I guess
no, this is everything.
everything. So all the
Everything is all within Tectonic.
Facebook, all the tweet, or all those messages, all these
Yeah.
stuff are hosted at this file system, commercial file
Yeah.
system. Everything that has to be worldwide, right?
So it's within each data center.
Okay.
Each data center so in order to the semantics of this file system are guaranteed within each data center. If you want to do like cross, region replication and things like that, you have to build additional layers of abstraction on top of it, and that's kind of up to the customer. But in terms of what this file system provides, it provides kind of an append only, kind of durable semantics within a data center level.
Okay, I'll let you go. Yeah, thanks. Yeah.
Yeah. But I think that's maybe the interesting part is, the Tectonic file system provides a very basic API. All of the different applications kind of build on top of this to build their logic into it. Yeah, and so kind of the second takeaway here is I don't really need to spend that much time on it here, but the pipeline needs to be optimized. And going back to this motivation point here is, why do we care about optimization is a really important question, right? And so the fact is that if we're able to improve the efficiency of storage or preprocessing, that gives us more capacity to use within the data centers to do more interesting things, right? Like training models, right? So if we're able to improve on these storage and preprocessing components, not only are we able to avoid stalling the GPUs and things like that, we're able to even just increase the overall number of GPUs that we have for training these models. And so let's start looking deeper into where can we gain some of these optimizations, right? Like let's start understanding what are the bottlenecks here. And if we start by looking at the reader tier, what we see is that, well, it's kind of hard to pinpoint a specific bottleneck. And to illustrate this, what I'm showing, again, are the 3 recommendation models. And on the y-axis is the percent utilization of a number of resources at one of these reading nodes, right? While training one of the models respectively. So what we see, for example, is when we launch a training job for RM1, right? And we're using one of these DBP readers to pre-process the data, that reader is bottlenecked by the CPU. For RM2, it's actually bottlenecked by the network. And for RM3, it's actually bottlenecked by the memory capacity. And even projecting towards the future, what we kind of expect is that memory bandwidth is going to become an issue. And so kind of, you may be asking well, you didn't really identify any bottlenecks, right? They're kind of spread everywhere. And that's one of the key challenges, is that because these bottlenecks are so diverse, we can't simply, design a new server SKU or a new server implementation with more CPUs or with more memory, right? And expect that to solve all the problems. These takeaways suggest that we need to focus on deeper kind of optimizations, both in hardware and in software. And so if we kind of look at and ask what are kind of the optimizations that we can do from a hardware perspective, well, the natural question is, we use accelerators for training, why not for data ingestion, right? The table to the right, what I'm showing are some common pre-processing operations used for these models, and to just give an idea of like what are possible avenues that people can start exploring to accelerate these models. There's lots of interesting challenges here from a research angle. A lot of these operations are not just general matrix multiplies, they're really diverse and have different hardware characteristics. There's a lot of systems challenges on top of that. For example, managing lots of different kernels, a lot of different memory characteristics for these operations, etc. I'm happy to talk more in detail, but for sake of time, just keeping it at a high level. From a software angle, what can we do, right? In the paper, we talk about a lot of different optimization techniques that we can do, such as your standard predicate pushdown, pushing filtering to storage, better memory codings and things like that. But in the second half of this talk, I'll go really deep into kind of this co-design angle. So I'll leave the details for there. Now let's take a look at the storage tier. And what we see in the storage tier is that it's really, really imbalanced. And so going back to this discussion on our storage tier, what I mentioned is that all of these data sets are stored in this distributed file system called Tectonic, right? And what Tectonic under the hood is just a bunch of hard drive based server nodes that's, stitched together with some upper layer metadata logic, right? But at the end of the day, it's all hard drives. And when we build a data center to train models, we need to provision our storage cluster to meet 2 demands. The first demand is we need to just store the data set itself, right? And so what I'm showing here in this table is the amount of power we need to provision enough hard drives to meet this requirement, right? So all of this is normalized, but what this is saying is that, okay, we need 1.0 units of hard drives to store our data set, right? But we also need I/O capacity. We need to be able to feed the data sets to the training jobs as they read them without, stalling, waiting for disks to spin and things like that. So what I'm showing here is, the amount of, again, normalized normalized hard drives that we need to supply enough I/O requirements to meet enough I/O demand, right? And of course, within our data centers, we need to meet both requirements. We need to store the data set and we need to provide enough I/O to feed the models, right? And what you can see here is that we're over provisioning storage by an order of magnitude to meet I/O demands, right? So if we had to buy, 1 terabyte of hard drives to store the data set, we need to buy, 10 terabytes of hard drives. Most of it is just empty space, but just to get enough, spinning disks to meet this I/O requirement, right? Which is hugely inefficient. You may ask, okay, well, there's things called flash, why not use those? And long story short is that flash kind of has the opposite problem. It's really I/O efficient, but it's not as dense. So we need a lot of storage capacity in order to if we were to put all of the data sets on flash, that would make the problem better, but it still kind of has this imbalance issue. At the end of the day, kind of what we think is the right approach is really this notion of composite storage, where we use hard drives and flash, right? Ideally, we should use hard drives to store the data set, and then all of the extra I/O capacity that's not met by hard drives, we should put on something that's more I/O efficient, such as flash, right? And to motivate this, to show that why we think we can do this is, well, we looked at how our data sets were being used. And so on the x-axis, what I'm showing is a CDF of the entire data set for each of these models with their bytes ordered by read popularity, right? The y-axis shows the total percent of storage IOPS that those bytes contribute to. I know that's maybe a bit confusing, but to give you a concrete point, what I'm saying here is that, 40% of our bytes on disk can serve over 80% of the total I/O demand. So there's this kind of power law distribution in terms of popularity for our data sets. And there's this key opportunity here to actually build something like this, right? Where we can supply I/O using flash for the popular portion of the data set, but use hard drives as the durable storage foundation, right? And so as a quick aside, this is actually what we did, and we launched via this project called Tectonic-Shift. So at a very high level, what we did here was, within a data center, we used to have this single tectonic cluster, right, that served as the storage layer for all of the services in our data in this data center. We put this additional shift cluster, which consists of SSD-based storage nodes alongside this tectonic cluster. Now training jobs via the DPP service can choose to read either from Tectonic or from Shift. Of course, the key challenge is that we want popular data to be in Shift, right? But of course, with any cache, how do you know if that data is popular? And kind of just to tease the key insight that we had with this project without going too much into the details, what we noticed is, if we apply this notion of kind of co-design, of looking at the picture end to end, we saw that, these training jobs have a data set specification, right? They'll tell us exactly what data they plan to read ahead of time. And if we're able to kind of plumb this information all the way through our entire pipeline back to the storage node, that kind of gives us oracular information about what training jobs want to read in the future. And so we're able to do some intelligent kind of prefetching or cache emission policies that lets us keep the hot data in this SSD cache. If you want to learn more about this, yeah, definitely I'm happy to chat, or please check out the paper. But kind of to tell you about the impacts of this, we deployed this. Yeah.
There's a question, Dave.
Oh, sorry.
Yeah, no worries. So you mentioned that in terms of the training jobs, that you're getting data that you're predicting to be used in the future. there's some concepts that we've learned that are not viable in terms of cache policy, such as optimal replacement policy. Is that something that you guys looked at? Because it kind of involves like how it's going to access that data in the future.
Are you asking about like what specifically is the cache policy, or like how close we are to optimal?
Yeah, like did you like consider optimal, I guess, in the cache policy?
Yeah, so I guess to answer that, let me tell you about what our cache knows ahead of time, right? So I kind of gave this notion of like we can be oracular in terms of knowing what data will be read in the future, and then do interesting things, right, at a pretty high level. Specifically, what our cache knows ahead of time is that when a training job is launched, right, these training jobs run for days or weeks or even months, right? When that job is launched, we know effectively what data it plans to read, and roughly at what time, right? Because it does a linear scan of the entire data set. And so what we do is we take all of the training jobs that are active at any given time in the data center, and we kind of break down this data set specification into buckets, right? So we split up our entire data set into a bunch of different buckets, and using this information, we kind of assign a priority to each bucket using this like future information, right? And then so we're able to kind of so we have a cache omission policy because the framework that we use, CacheLib, pretty much just lets you just omit, like it gives you a cache omission policy, right? And so our policy is that depending on what the priority of each bucket is, we decide to omit that data into cache or just not. So it's not exactly kind of like the optimal, OPT policy, but it's kind of leveraging what will be read in the future to do this omission. It's a bit hard to compare exactly to OPT because it's also an eviction policy, but I don't know if that answers your question.
No, yeah, that does. I can imagine it's way more complex than that. So that's pretty cool. Thank you.
Yeah, kept that at a pretty high level, so sorry for that. Yeah.
So the cache is what exactly this is cache? It's not the page cache, right? It's not like in memory kernel page cache, and I guess this is the cache entry. I mean, is like what specific elements is that? Is it one block, and what size? What
Yeah.
exactly block it is? Probably is a table, right? Is that table?
Yeah, that's a great question. So to just answer that question, what we cache,
because feature, there's all different level file system. There's page level cache, but there's a
So we cache byte ranges in columnar files to answer the question and to kind of understand why our Hive tables are stored as columnar files, right? So within each of these tables, a column's worth of data is laid out contiguously adjacent to each other, right? And kind of the popularity that we see is within feature levels or within columns of our table, right? So maybe column A is popular, column B is not popular, column C is popular.
I think it's more like, I know, yeah, I see. Yeah. It's like a database. It's inside the database level, right? You have this kind of column file cache something. Yeah. Okay. So you're able to get the semantics, because if you look at the HDD, SDD, this low level, you don't have the information about the semantics. You have the 1010 this, but exactly. I don't think you're working at that level, right? That's very different.
Yeah, a higher level. Yeah, exactly.
High level. Okay. Yeah, it's more like application database cache. Yeah. Okay. Thank you.
Yeah, to just kind of wrap up this little short segue, we deploy this it works. We are able to see a lot of power savings. You know, in this short trace here, Shift is able to save 29% of power. And if you scale that up to a Meta data center, that is a huge amount of capacity savings. But kind of to circle back, oh, I guess the last thing I should say is that, you know, this is not the final, you know, like the best solution. I think there's a lot of interesting questions I'm happy to, you know, kind of talk about, brainstorm more about in the ML data caching space. But quickly, just to wrap up this half of the talk, kind of the fifth takeaway that we noticed was really that, you know, what's unique about industry ML deployments? Like, what new challenges does it bring? And really the biggest factor here is really scale. And scale translates to like diversity of a lot of different systems characteristics. So again, if we look at the data set size, they're really different. If we look at, you know, how much IO they need, they're really different. User behavior is also really different. So this trace is showing over the course of a year how much compute training jobs launched by users, you know, needed. And so there's lots of peaks and troughs corresponding to, you know, people on, you know, Christmas or something like that. And so ultimately, from a systems designer perspective, is how do you build a data center? How do you provision one to accommodate for all of this variation, right? And then, you know, as our discussion alluded to earlier, this is global, right? There's lots of data centers that are training jobs around the world. How do you manage scheduling, job placement? You want to co-locate your data right by your training job, right? So you're not sending terabytes of data per second under an undersea network, which is horribly inefficient. So how do you do all of this scheduling and things like that? And so there's lots of open questions here from a research perspective on, you know, how do you manage global training? And kind of to wrap up this point, you know, what can we do as researchers to just start answering these questions? And I think the biggest challenge here is kind of representativeness. And this is something that's being more and more of a problem, for example, with LLMs, even recently, where, you know, what academics are working on is really a different picture than what's deployed in industry. So as I talked about earlier, what, you know, is done for MLPerf is different from what's done at Meta, right? So, you know, starting to reconcile these two different worlds is really kind of the first step that we need to take. And of course, happy to chat more about kind of the potential solutions there. But yeah, just to wrap up this section, I kind of highlighted what are some of the key takeaways from looking at this DSI and training pipeline deeply at Meta.
So can I have another question? Like, because I'm interested in but caching. If you go back, that because you know the people know, you know, if you do the training for the convolutional neural network, like computer vision stuff, it's more like a streaming, and for doing the training, you know, it only have one scan, full scan, or you know the at most, because it takes forever, right, to do even the full scan of the image net. So the locality is not going to be very high, you know. And so I'm curious, your workload is some kind of different from the object detection, right? Classification, looks like.
Yeah,
So,
that's a really great point. And I probably should have mentioned this, but kind of the locality that we see here, okay, maybe I won't go there. The locality is not within a training job, right? Because we have that exact same characteristic that you mentioned, right? Our training jobs use one epoch, meaning that they scan the data set one time and there's no data reuse. The locality is really across training jobs. So for example, people will do things like hyperparameter tuning jobs, where they'll take the same model architecture and tweak like one or two different parameters within that model and then launch, you know, 10 jobs for that model, right? And all of those 10 jobs are reading the same data. And kind of what we're caching here is we want to store the same data that is being used by all of those 10 jobs, if that makes sense. So it's kind of
you have a multi-talent, like
yes, exactly.
Yeah,
exactly.
Okay, thank you.
All right, so I know, there's about, I think, 20 minutes left. So let me quickly go over kind of the second part of this talk, which is now that we kind of understand what DSI is, what can we do to optimize it? And I want to circle back and just highlight, like, we need to look at the end-to-end pipeline and really consider optimizations across this entire pipeline, right? So with recommendation jobs, what we see is, to just recap what this pipeline looks like, users will request recommendations to an inference tier. This inference tier will fetch data, fetch features describing the user's interests from a feature store, perform the recommendation, return the result, right? But that's where kind of this entire pipeline really starts. What the inference tier will do is send the features that were used for recommendation and the outcome of the recommendation, for example, if the user likes the post or not, to a feature engineering pipeline. These are, again, are the Spark jobs and things like that will generate these massive training data sets, Hive tables stored in a storage tier. And then for each training job, right, we have this reader tier and then the training tier, which produces the models. So kind of the crux here is that we need optimizations across this pipeline to get the best results. And the motivation behind this, where we kind of started with this project, is let's look at how these data sets look like in terms of the actual data itself. And what we quickly notice is if we look at how each sample is being generated, what happens is, let's suppose Alice is, requesting some recommendations for Instagram, right? So we'll fetch a sparse feature that describes Alice's interests. For example, her last and liked post IDs. We'll perform inference on that, produce a recommendation. And what's stored in the data set is this input sparse feature, right? So a big, vector of IDs that describe Alice's interests and maybe a label, for example, 0 for no like. But Alice typically, browses multiple posts. And what happens is that because she didn't like one of these, she didn't like the previous recommendation, the input is exactly the same. And what's stored in the data set is exactly the same, right? You can kind of see where I'm going with this, where someone scrolls through Instagram and sees dozens of posts. This feature column, which is the vast majority of the data set in terms of bytes, stays pretty much static. And even if Alice does like a feature, what happens is the one value is changed. For example, she has a new like, right? So we prepend one integer into this big list, but the rest of the values are still exactly the same. And so kind of the intuition here is if we look at these sparse features, these categorical features, which describe, users' interest and features about the item, they're very infrequently updated across all of the training samples corresponding to a given user, meaning that these data sets are very highly duplicated. And so there's lots of different types of sparse features. For example, the last and like post IDs was just a concrete example. And this is something that we validated in production recommendation data sets. And kind of the high level one sentence takeaway is that 81.6% of bytes correspond to exact duplicate rows in the data set, right, for that feature column. Where all the values in that list were exactly the same as another sample in the data set. And so you can think of how many resources are spent storing the data, pre-processing the data, training over the data, that are being wasted because of they're just spent processing duplicate results, right? And so our solution to this issue is a project called Rect, and Rect is just essentially a suite of optimizations. And the key insight is that we really needed kind of co-designed optimizations across this entire pipeline in order to get this to work, where we need some upstream optimizations in order to get downstream optimizations to actually even function. To give a concrete, description of this, we first started in storage at the very high upstream of this entire pipeline, and we needed to coalesce duplicate samples together to maximize their deduplication potential, right? Because everything downstream works in terms of batches. So if you don't have any duplication in your batches, then there's nothing you can do. Then during pre-processing, again, training jobs don't understand database rows, they understand tensors. And so we had to come up with a new tensor encoding that allows us to, now that we have a lot of duplication in each batch, we need to encode that tensor to effectively, deduplicate it, right? Because even if you have a lot of duplication and you just stuff it all in a tensor, you don't get any benefits. And finally, during training, now that we have this better deduplication representation of a tensor, the models itself, the PyTorch modules need to understand that. So Rect presents new DLRM PyTorch components that allow us to get the benefits of these cool new tensors. So to dive into kind of the details here, and again, please feel free to interrupt. Where we started again is with storage, right? The goal is to maximize the deduplication potential here. And the issue here is that even though I showed you that there's a lot of duplicate samples for a given user, the issue is that there's billions of users, right? So all of the duplicate samples are interspersed across this entire massive data set with a lot of different other users, right? So we want, in this picture, what we want is, all these blue stripes are all duplicates, right? We want them to be close to each other effectively, but by default, they're not, because there's so many different users with all of their different unique characteristics. And kind of what we did here was we just added this clustering operation as part of the ETL pipeline, which now groups together all of these duplicate samples together in our data set. And a very direct immediate benefit that we get from this is, as I mentioned before, we store these data sets in columnar files, right? And these columnar files have compression blocks. And so now that we get all of this duplication into these compression blocks, we just apply Z standard basic black box compression techniques, and we get massive data set size savings just by adding this upstream operation. On top of this, when we read these batches from over the data center network, all of these mini batches, right, that are being read are still compressed. So we get a bunch of network IO savings as well while reading all of these mini batches. So just by adding this upstream operation, we get storage, we get data reading benefits via compression. So the next point is, okay, we get good compression using things like Z standard compression, but tensors aren't compressed. So again, what can we do here? And in terms, and I want to give a bit of background about how PyTorch, how recommendation models represents these sparse features. And so we use a tensor called a keyed jagged tensor, right? And so for a batch of 3 sparse features, 3 rows here in our data set, how we encode this as a tensor is using this keyed jagged tensor, where we flatten all of the vectors into one flat vector, and then we encode the offset index into this vector for each row using a separate vector, right? So to give a concrete point, the last row here has an offset of 6, which points to these values 3, 4, 5, which encode the original row, right? And then so this is what is pre-processed and finally sent to trainers, and what trainers understand. So how we deduplicated tensors was through this new encoding called an inverse keyed jagged tensor. And at a high level, we just add another layer of indirection, right? Like that's one of the solutions to any problem in computer science is another layer of indirection, where we have this inverse lookup tensor, which now points to the corresponding offset value for each row. So the last row here has an inverse lookup of 0, which points to an offset of 0, which points to the original values here. So all of the 3, 4, 5s in this batch are just represented once in this tensor, right? So, in this example, it's like 66% reduction or whatever in size, but you can imagine these batches are thousands of samples large, and then the size of each of these vectors again are thousands. So you immediately get a lot of benefits here. And the last point, is we can leverage this to improve GPU efficiency as well. These tensors can directly provide us GPU efficiency. And how we're able to do that is through new modules in our recommendation models, right? And so again, to give some background, how we train these models is through synchronous model parallel and data parallel training. I'll focus on the model parallel part because that's where these sparse features come into play. But what we see here is, we shard these embedding tables, these embedding operations across a bunch of different GPUs because they can't fit in one GPU, similar to how LLMs work, right? And so when we train these models, each GPU will get a batch of all of the features. And the first thing that we'll do is we'll send all of the features to the right GPU. So this GPU1 holds embedding table 1. So all of the GPUs will send feature 1 that it has to the first GPU. We'll group all of this together into a global batch, perform an embedding lookup. Again, very similar to how LLMs work. We'll take each categorical value, look up in an embedding table a multi-dimensional representation of the inputs, and then finally we'll pull together all of the different samples together. So, for example, we might take the vector average or sum or something like that of all of the different inputs into all of the inputs of the pooling operation. Then we'll send back this, pulled output back to the original GPU, and we'll just do backprop as normal, right, downstream. So very quick intuition on why Rex improves performance is, well, the inverse key jagged tensor values are just smaller, right? So what we introduce is just plug and play modules that you can swap out, for example, an embedding operation or pool operation, and it knows how to decode this inverse key jagged tensor. And so we're able to save network capacity, for example, because we send less data over the network. We do fewer embedding lookups, we store fewer activations, and then we're able to even deduplicate compute. For example, if we have to sum the embedding vectors for 3, for 4, for 5 during a pooling operation, we know that we only need to do this operation once, right? And then we can broadcast the result of that pooling to the other rows in the batch. And yeah, that magically just gives us a lot of savings. And so kind of to summarize all of this is by doing all of these optimizations that build one on top of the other throughout this pipeline, we're able to save tremendous amount of efficiency in terms of storage compression ratios, reader throughput, trainer throughput throughout this entire pipeline. And I have a breakdown of why we get specific wins, but for the sake of time, maybe I'll just I'll skip them, but happy to answer any questions there. Just to summarize, I think what I've talked about in this talk is, what does an end-to-end training deployment in an industrial landscape look like, right? And then what are some of the key challenges in terms of scaling these systems up? right? And so kind of the takeaway here was, hey, it's not just GPUs, there's lots of different components, and we need to think about, how all of these disaggregated storage, ingestion, and training components fit together within this entire pipeline. And then in the second half, I kind of talked about how, what are some key ways we can optimize efficiency of this entire pipeline. And that's with thinking about it, in a holistic lens, right? Like looking at the problem, not just from a storage engineer's perspective or from a GPU engineer's perspective, but kind of combining and building optimizations one on top of each other. Yeah, I just, acknowledge a lot of great collaborators at Meta and at Stanford. And thanks so much for your time.
Thank you for the great talk, Mark. So any questions? No, you're running out of questions. So Mark, I have a question for you. So
yeah,
you mentioned that the hardware software co-design could be a potential direction, but one sort of the challenges saying in the cloud is you have thousands of 10,000 of machines. So in those cases, every possible design choices you made in the hardware might have a big impact, no matter its actual performance or economically. So in this case, what do you think, let's say, how to balance the weight, the ratio of modification on the hardware side and the software side?
Yeah, that's a great question. And I don't know if anyone has a good answer to that. I mean, I can kind of go in two directions here. One is, what if we go down to the very, very low level operations that are taking up a lot of resources, what are they, right? And understanding that from kind of a first principles is how we can start reasoning about this. And what we've seen actually is that you might have talked about this notion called like data center attacks, right? Those operations are a huge component of the overheads in terms of storage and data reading. So things like, everything is an RPC, right? So it's all serialized, deserialized on thrift. Everything is encrypted. So all of those components, right, contribute massively to the overheads. And that's just something that you have to live with to build a application that's deployed, globally. And so, there's this really awesome paper called Accelerometer and ASPLOS that talks about a lot of this. And I think, still just echoing that point of like, there's just core operations that are super expensive, but addressing those can have benefits not just for training, but, pretty much in any application in the data center. So I think that's like kind of the low hanging fruit. But in terms of, the ML specific operations, yeah, I think, we shouldn't design something that will be, useless if we come up with a new model, right? Like we want something that works like kind of by the Amdahl's law principle, where like we want to target the largest proportion of expense in the model. And I think maybe a good approach that I've seen taken with this is how the TPU team has gone in this direction, right? Where like if you take a look at the first TPU paper, one of the things that they focused on was like, hey, here is a characterization of all of the different models that run in our data center environment. Like, X% are CNNs and Y% are like NLP models. And I don't exactly remember the exact models, but kind of that characterization driven approach where, so now we'll design an accelerator that speeds up, DNNs by this much and NLP by this much and kind of like do that analytical process. And as things have shifted, they've kind of changed what they focused on, right? So, recently they've been going towards like optical interconnects to handle these scale out, distributed training cases. So I think like And it was a very long-winded answer, but going with the kind of a characterization-driven approach first, and then building an analytical model, and then like that informs if it's worth building a new piece of hardware, I think is probably the right approach.
Okay, cool. Cool. Any other questions or from online audiences?
I just wanted to thank you for coming in. I really enjoyed your presentation.
Yeah, thanks so much.
One last one from my end. Just as a curiosity, have you guys ever considered using things like FPGAs to accelerate any parts of the system, or at least on the hardware side?
Yeah, I mean, like there's two dimensions of like, you know, has Meta ever considered, and I don't know, and I can't speak for them. I definitely think, you know, things like SmartNICs, especially if you take a look at the direction that Microsoft has headed in, again, addressing like, you know, the data center tax operations, right? Where can you do things, you know, at line rates in the NIC itself? Or presents a lot of cool opportunities, but I personally haven't looked into using SmartNICs in my own research, and I don't know about Meta, and I can't speak to that. So
Yeah, no worries. Awesome. Thank you.
Cool. So I think that let's thank Mark one more time.
yeah,
Well,
thank you,
sure.
everyone.
And thank you for a great talk, and hope to talk with you later.
Yeah,
Okay.
feel free to
great.
reach out.
Yeah,
Thanks.
sure. Take care. And thanks everyone for being here. And one last note for the course student, we will have a paper presentation on Wednesday. Don't forget about that. And yeah, I think that's it. So see you guys next time.
Thank you.